Welcome you in the lecture series of quantum computing. This is another lecture on Introduction to Quantum Mechanics. In previous lecture, we have discussed about eigenvalues, eigenvector, eigenfunction, and spectral decomposition of an operator. In this lecture, we will discuss about spectral decomposition again, tensors and tensor product, and direct sum. We know from previous lecture, in spectral decomposition, any vector or operator can be written as this is a vector operator, and operator A can be written as sum of the eigenvalues into corresponding outer product of eigenvector. Here lambda I is the eigenvalue and Vi is the corresponding eigenvector. If we consider poly X matrix, and we know poly X matrix in Z basis or computational basis can be written as 0, 1, 1, 0 with computational basis cat 0 and cat 1. This is poly X matrix. And this is not diagonal. In spectral decomposition, if I consider this poly X matrix or this X operator, we can find out the eigenvalue of this operator. It will be lambda 1 is equal to 1 and lambda 2 is equal to minus 1. And corresponding eigenvectors are ket plus and ket minus. So in spectral decomposition, the poly X matrix, it can be written as eigenvalue and outer product of corresponding eigenvector plus eigenvalue and outer product of corresponding eigenvector. And poly X matrix in X basis, it is 1, 0, 0, minus 1 with the X basis. And this is diagonal. And the eigenvalues are at the diagonal. So diagonal elements are the eigenvalues of this poly X matrix, and the bases are the eigenvectors of this poly X matrix. So here we can see in natural basis or quantum basis cat 0, cat 1, the poly X matrix is not diagonal. And if we do the spectral decomposition, then poly X matrix will be diagonal. So if we consider natural basis or Z basis or computational basis, this is cat 0 and cat 1. In spectral decomposition, these computational bases are changed into the X basis, cat plus and cat minus. These are the X bases. In Z basis, the poly X matrix is represented as with element 0, 1, 1, 0 with natural basis. And in spectral decomposition, the poly X matrix will be the diagonal matrix where the diagonal elements are the eigenvalues. In computational basis or Z basis, the qubit is the superposition of the natural basis. So here qubit, it will be the superposition of quantum basis cat 0 and cat 1. So psi is alpha cat 0 plus beta cat 1. And in spectral decomposition or in X basis, the qubit is the superposition of the X basis. So here qubit psi, it will be represented as alpha cat plus beta cat minus in spectral decomposition. Here cat 0, it is represented in matrix form as 1, 0 and cat 1 is represented as 0, 1. In spectral decomposition, cat plus, it is represented as 1, 0 and cat minus, it is represented as 0, 1. And in Z basis, cat plus is represented as 1 by under root 2, cat 0 plus cat 1, and cat minus is represented as 1 by under root 2, cat 0 minus cat 1. And in X basis or spectral decomposition, cat 0 is represented as 1 by under root 2, cat plus cat minus, and 1 is represented as 1 by under root 2, cat plus minus cat minus. In Z basis, if I apply poly X matrix on cat 0, it will flip the qubit. Means if I apply X gate or poly X matrix on cat 0, it is cat 1. And if I apply poly X on cat 1, it will be cat 0. So it behaves like bit flip. In spectral decomposition or X basis, if I apply the poly X in spectral decomposition form on cat plus, it will be poly X in spectral decomposition. It is 1 0 0 minus 1, and cat plus it is 1 0. So here it will be 1 0. It is cat plus. And if I apply poly X on minus and poly X in spectral decomposition, it is 1 0 0 minus 1, and minus is 0 1. So here we will get 0 minus 1, or I can write minus minus. So here we can see, if we apply poly X on cat plus, I will get cat plus same. And if I apply poly X on cat minus, I will get minus cat minus. So in Z basis, the poly X matrix behave like a bit flip gate, but in X basis, the poly X matrix will behave like a poly Z gate in Z basis. So here poly X, it will behave like poly Z in Z basis. So here we can see Z basis is converted into X basis if I will take the spectral decomposition of the Z basis. So here Z basis means cat 0, cat 1 are changed into cat plus and cat minus. So the quantum basis cat 0, cat 1 are changed into quantum basis cat plus, cat minus. This Z basis to X basis transformation is basically the Hadamard transformation. Means if I apply Hadamard on 0, I will get cat plus. And if I apply Hadamard on cat 1, I will get minus. So similarly, with measure poly Y or spectral decomposition of poly Y, the quantum state psi is represented as alpha cat I plus beta minus cat I. Means the quantum basis cat 0 and cat 1 are changed into cat plus I and cat minus I. And this kind of transformation is known as phase plus Hadamard transformation or SH transformation. Means if I apply SH on cat 0, I will get plus I, and if I apply SH on cat 1, I will get minus I. And similarly, with measure poly Z or spectral decomposition of poly Z, the quantum state psi, it is represented as alpha cat 0 plus beta cat 1. And this is generally we use the Z basis or computational basis for our computation. So in summarized form, we can say with Z basis or computational basis cat 0, cat 1, the quantum state psi is represented as alpha cat 0 plus beta cat 1. This is the superposition of Z basis cat 0 and cat 1. And with X basis or cat plus cat minus, the quantum state psi is represented as alpha cat plus plus beta cat minus. And this is the superposition of the X basis cat plus and cat minus. And with the Y basis or cat plus I and cat minus I, the quantum state psi, it is represented as alpha cat I plus beta minus cat I. So this is for the Z basis, and this is for X basis, and this is for Y basis. And now tensors and tensor product. Tensors are the mathematical objects that are used to describe physical properties such as electricity, electrical conductivity, and in physics. Tensors obey certain transformation rules about the physical property they represent and are considered generalization of scalars, vectors, and matrices. A scalar is a tensor of rank or order 0. A vector is a tensor of rank 1. The rank of a tensor is the number of directions required to describe the object it represents. So the tensor is a multi-dimensional array of complex numbers that can represent quantum states, operates, or measurement when systems are combined. The tensor product is also known as Kronecker product or the direct product. If we are having two systems, A with state cat V and system B with state cat W, then the joint state psi, it will be the tensor product of these two states V and W, and this is the tensor product. And the state V, it can be represented as the linear combination of the quantum basis. Here cat I is the quantum basis for the quantum state V, and J is the quantum basis for the quantum state W, and this is tensor product of both. Now I can write it is summation I1 to n and J1 to n Vi into Wj, and tensor product of the quantum basis cat I and cat J. So this is overall quantum basis for cat V tensor cat W. So here, if cat V is represented as column vector V1, V2 to Vn, a matrix of size n is to 1, and W is the matrix W1, W2, Wn, the size of m into 1. Now the tensor product, it will simply multiply first element of V with all elements of W. So V1, W1, V1, W2 to V1, Wm. And after this, multiply V2 to all the elements of W. So it is V2, W1, V2, W2. So, and we go up to Vn, Wm. So the matrix of this tensor product, it will be of the size mn into 1. This is a tensor product, and the result is a rank 1 tensor or vector in a large Hilbert space. So tensor product is a way of putting vector space together to form a large vector space. This construction is crucial to understand the quantum mechanics of multi-particle system. Finally, we mentioned the useful notation here, psi tensor k and tensor k in the power form. The meaning of this is that psi is tensored with itself k times. For example, this psi power tensor 2 means psi is tensored with itself. And if I write psi power tensor 3 means psi is tensored itself 3 times 1, 2, and 3. The tensor product is useful in quantum computing. So if I am having a system which is having qubit A and qubit B, and I apply the identity gate on qubit I and poly X gate on qubit B, then the final state psi, it is represented as I tensor X AB. So here the input, it is simply the tensor of A and B, and it is written as cat AB. This is a 2 qubit system, and output qubit psi, it is simply the tensor product of these two gates I and X multiply the 2 qubit input cat AB, and we will discuss these kind of quantum systems later. Now here, if we consider cat 0, it is represented as 1 0, and cat 1, it is represented as 0 1, and quantum state psi, it is represented as alpha cat 0 plus beta cat 1 in Z basis or computational basis. And if alpha 1 and beta 1, then the quantum state psi, it is cat 0 plus cat 1. And if alpha 1 and beta 0, then the quantum state psi, it will be cat 0. And if alpha 0 and beta 1, then the quantum state psi, it will be cat 1. Now, if I want to find out cat 0 tensor cat 1, and cat 0 is 1 0, tensor cat 1 is 0 1. So it will be this 1 is multiplied with the all elements of 0 1. So 1 multiply 0 0, 1 multiply 1 1, and after this 0 is multiply 0, and 0 multiply 1, it is 0. So you can see here cat 0 is of size 2 is to 1, cat 1 is also of size 2 is to 1, but the tensor product of cat 0 and cat 1, it is of size 4 is to 1. Now another example, if cat v is 1 2 and w is 3 4 and 5, find the tensor product of cat v and cat w. So here the tensor product of cat v and cat w, it will be 1 2 tensor product of matrix 3 4 5. So it will be here 1 is multiply 3, 4, and 5. Now 2 is multiplied here. It is 6, 8, and 10. And this is of size 6 is to 1. Now the tensor product of 2 is to 2 matrix. So if I am having a matrix of size 2 is to 2, it is A, B, C, D, and another matrix of size 2 is to 2, E, F, G, H. And we will take the tensor product of these. So here, with the first element is multiplied with this matrix. So I will get AE, AF, AG, and AH, these four elements. And B is again multiplied with this matrix BE, BF, BG, BH. And similarly CE, CF, CG, CH, and DE, DG, DH, and this is DE, DF. It is 4 is to 4 matrix. Now let us take another example. The quantum state cat psi is represented as 1 by under root 2 cat 0 plus cat 1. Find out the tensor product of itself with order 2 and tensor product with itself of order 3 explicitly, both in terms of tensor product like cat 0, cat 1, and using the Kronecker product. So here the quantum state psi, it is 1 by under root 2 cat 0 plus cat 1. I can also write it as 1 by under root 2 1 1, and this is for the basis cat 0 and this one is for basis cat 1. Now the tensor product of order 2, it will be the tensor product with itself, and it will be 1 by under root 2 1 1 tensor 1 by under root 2 1 1. So it will be 1 by 2 1 1 1 1 of size 4 is to 1, and this one is for basis cat 0 0, this is for cat 0 1, this is for basis cat 1 0, and this is for basis cat 1 1. So here in psi there are two bases cat 0 and cat 1, but in tensor product of order 2 it is having four bases, and I can write this as 1 by 2 cat 0 0 plus cat 0 1 plus cat 1 0 plus cat 1 1. So there are four bases in the tensor product of order 2. Similarly, the tensor product with itself three times means tensor product is this, and this will be 1 by under root 2 cat 1 1 tensor 1 by under root 2 cat 1 1 tensor 1 by under root 2 cat 1 1. So we will get here 1 by 2 under root 2, and it will be of size 8 is to 1 1 1 1, and there are eight bases for this tensor product. It is 0 0 0, it is 3-qubit system basically. 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and this one is 1 1 1. Or I can write it as cat 0, cat 1, cat 2, cat 3, cat 4, cat 5, cat 6, and cat 7. So we can see psi is having two quantum bases cat 0 and cat 1, but the tensor product of its with itself three times, it will give you the eight quantum bases. And this was the example of textbook Nelson Choing. Example was 2.26. Another example from the Nelson Choing, it is 2.29. So that the tensor product of two unitary operator is unitary. If I consider two unitary operator A and B, and if they are unitary means A dagger, it will be equal to I, and B dagger, it will be equal to B. And we know A tensor B dagger, it is simply A dagger tensor B dagger. We can write equal to this. Now, if I want to prove the product of two unitary operator is unitary, means we have to prove the tensor product of two unitary operator is unitary, then this should follow this property A tensor B dagger, A tensor B. It will be identity. Let us check this. So here A tensor B dagger into A tensor B. I can write it as a dagger tensor B dagger into A tensor B, and it can be written as A dagger A tensor B dagger B. And you know A and B are unitary. This means this one is identity matrix tensor. This one is also identity matrix, and tensor of identity matrix and identity matrix, it will again identity matrix. If this matrix is of size 2 is to 2, then the matrix will be of the size 4 is to 4. So from here we can see that the tensor product of two unitary operator is unitary. Now another example is 2.30, so that the tensor product of two Hermitian operator is Hermitian. If I'm considering here two operators A and B, and if they are Hermitian, then A dagger will be equal to A and B dagger will be equal to B. So the tensor product of two Hermitian operator is Hermitian. Means we have to prove that A tensor B dagger, it will be equal to A dagger B. If this one, then we can say that the tensor product of two Hermitian operator is Hermitian. So let us check. If I write this, it is A dagger tensor B dagger. And you know A and B are Hermitian, then A dagger can be written as A and B dagger can be written as B. So from here we can say A tensor B dagger, it will be equal to A tensor B. So this is Hermitian. So the tensor product of two Hermitian operators is Hermitian. Another example 2.36. So that the polymatrix except for identity matrix have trace 0. You know polymatrix X, it is with element 0, 1, 1, 0. Here we can see the diagonal elements are 0, 0. So sum of the diagonal elements is 0. So it is traceless. Similarly, poly Y matrix having the element 0 minus I 0. Again, you can see the sum of the diagonal element is 0 again. So this is again having trace 0. So trace of X is 0 and trace of Y is also 0. Similarly, Z matrix, it is having the elements 1, 0, 0, minus 1. So again, the sum of the diagonal elements 0. So trace of Z is again 0. So the poly matrices are having trace 0. Here on other side, identity matrix, it is 1, 0, 0, 1. And you can see the sum of the diagonal elements. So trace of identity matrix, it is not equal to 0. Now let us consider two bases plus and 0. If I want to find out the tensor product of these two, so here the plus is represented as 1 by under root 2 cat 0 plus cat 1, or I can write it as 1 by under root 2 1 1. And you know cat 0, it is represented as in matrix form 0 1. So now the tensor product of cat plus and cat 0, it will be 1 by under root 2 1 1 tensor 1 0. So it is 1 by under root 2 1 0 1 0. This is for basis 0 0 0 1 1 0 and 1 1. So I can write it as 1 by under root 2 cat 0 0 plus cat 1 0. Only these two are having the probability amplitude. Now similarly, find the tensor product of plus and minus. So you know cat plus is represented as 1 by under root 2 1 1, and cat minus, it is represented as 1 by under root 2 1 minus. So the tensor product of cat plus and cat minus, it will be 1 by under root 2 1 1 tensor 1 by under root 2 1 minus 1. So it is 1 by 2. This one is multiply in this matrix 1 minus 1 1 minus 1. This is for the quantum basis cat 0 0. This one is for quantum basis cat 0 1, for quantum basis cat 1 0, and for quantum basis cat 1 1. So I can write this tensor product as 1 by 2, and this is having 4 quantum bases cat 0 0 minus cat 0 1 plus cat 1 0 minus cat 1 1. So the tensor product having four quantum bases cat 0 0, cat 0 1, cat 1 0, and cat 1 1. And this tensor product is written as 1 by 2 cat 0 0 minus cat 0 1 plus cat 1 0 minus cat 1 1. Probability amplitude of cat 0 1 and cat 1 1 is minus 1. So that's why here minus sign. Now direct sum. We know that the vector can be described in terms of basis vector. Let two vectors v and w that can be expanded in some orthogonal basis I and j. So cat v, it is represented as orthonormal basis I, it is vi and quantum basis I, and w, it is represented as j12 n wj cat j. Or order may be different, it is 1 to m, I can write. If we defined m plus n basis vectors, then we say that the vectors spanned by the basis vector is cat v plus cat w, and this is known as the direct sum. So suppose we are having the quantum state cat v in column vector as element v1 v2 to vn, and w having the elements w1 w2 to wm. Then the direct sum of these two quantum states cat v and cat w, it is simply first we write the elements of quantum state v, then we will write the elements of quantum state w. This is simply a direct sum. So here, this is not like as usual matrix sum. This direct sum here v1 to vn plus w1 to wm, and it is not equal to v1 plus v1 to vn plus vm. This is not equal to as just like in classical theory. In direct sum, it is basically we will write first the elements of the quantum state v, then we write the element of quantum state w. For example, if we are having quantum state v in the column vector as 1 2 and quantum state w with element 3 4 and 5, find the direct sum. So here the direct sum of quantum state v and w, it will be first we will write the elements of quantum state v, these are 1 and 2. Then we will write the elements of quantum state w 3 4 5. So these are the elements of the direct sum of v and w. So direct sum of two vector or two quantum state is different, just like in classical theory. It is not as in classical theory we where we directly sum up the elements, but here we will not sum up the elements, we will just list the element. First we list the element of first quantum state, then we will list the element of quantum state second. And this is the end of this lecture. In the next lecture we will discuss quantum computation with single qubit gates like poly X gate, poly Y gate, poly Z gate, Hadamard gates, and also we will discuss the concept of Bloch sphere. Till then, thank you.